So I think what we'll do is we'll have 15 minutes for each group to report back and to field questions. And we will start with the dust precipitation group, led by Guillaume Gronoff and Bill Moore. And I think Guillaume is going to be the one to report back. So I'll just go ahead and hand the mic over to him.
Okay, fine. Okay. Well, I don't have a big, nice presentation to project here because it would have taken too much time out of our group to present it. And we had a very interesting discussion up until the very end of the session, and we almost wanted to get 2 hours more to finish that correctly. So. In the question of the dust precipitation in the planetary atmosphere and in the solar system, we found some 4 main questions that we think is important to address to better understand our planetary and exoplanetary environment and how they can evolve with time. So the first big question we had is what is the history of dust in the solar system? Dust can precipitate on planets and did precipitate on planets and had a lot of effect. And the problem is what was the frequency of the dust precipitation and what was the mass distribution of that dust precipitation in the solar system. So this is the first big question to answer. It involves a lot of other questions. Where does that dust comes from? Interplanetary particle dust or some more warped dust? And how can we answer these questions? We know that modeling can help us understand that. We have observation of analogs of the solar system that could help us better understand that dust. But it asks, of course, the other question, how can we really extrapolate our solar system to other solar systems? And on that big question of the history of dust, we have all the observation in the solar system of isotopic ratios that can be quite strange compared to the sun isotopic ratio, and we need to understand that that history. So that is the first big question, and that first question led us to look at existing observation of dust environment around other stars and with exoplanets. And so Paul gave us a very nice talk about how the different imaging systems observed some planets crossing dust belts. So some exoplanets are able to cross dust belts, and we see some variation in optical of their emissions. So the question is that can we understand the effects of these planets crossing dust belts? So that is the second question. So it will involve a lot of modeling and comparison with the observations that we have. So it's really nice because we already know that it exists and we already have all this observation. So now we need to do the hard work, the modeling, and the comparison over there. The third question, it's a little bit more within the history of the planets. We know that all this dust fall on the planet and bring organics and volatiles. So the question is how can we understand the deposition in time of these organics and volatiles, and can we understand their effect and their importance in the creation of the planetary atmosphere? Some of the points we had concern some of the very recent papers that say that the first volatiles that we brought on the forming planets evaporated very fast, and within a few million years we had nothing. So we needed to bring new volatiles, and this dust could bring those. And the fourth question that we have is, can we understand the effect of the dust precipitation on the climate? Because the later dust will arrive at already existing atmospheres, and that can have a lot of effect on the atmosphere. So it rains out first, so it can create clouds at different altitudes, and that has different effects on the climate. And then we have the effect on the upper atmosphere, because dust falling on the upper atmosphere can heat up the upper atmosphere and can have some effect over there. Through all the discussions, we basically discovered that everybody had a very good insight on a very small part of the problem, and that was one of the big point of our hacking group. We had to explain to each other a lot of the things that we knew only on our point. And the conclusion of that is we need to be a little bit more, to synthesize our knowledge of this effect. And so we decided that we'll first create a white paper to summarize what we know and what are the big questions and what are our capabilities currently and what we want to do in the future. From that white paper, the objective is to create a workshop, and then having at least a review paper of all the work that has been done there and all the work that can be done in the future on that subject. So, do you have any questions? Have been that clear? Wow. Yeah. Okay. Yeah. Yeah. Yes. So, well, dust and
Repeat the question.
Yes. So the question is, what is exactly the definition of dust we have? So, is it only? So it would be a micrometeorite and up to the comets. So object able to bring volatiles quite easily to the bodies. Any person has some insight on the subject, and I guess that some people were in other sessions on the GWST and may have some knowledge about dust precipitation. Nobody? Okay.
Okay, very good. Thanks. All right, next up we have Daniel Apai. Leslie, are you going to present?
Thanks. So Dan Apai and I co-chaired a hack, and here we were hacking a potentially habitable planet. And so part of the goal here was to assess, say, NExSS had access to a very powerful optical infrared telescope. Sorry. And we had a single small planet in the habitable zone of a sun-like star. What observations would we like to get, and how would we prioritize those observations? And what do we need to do now to prepare in the future down the line when we are at the point of characterizing potentially habitable Earth-like planets, that we're prepared to interpret the data? So we had over 20 people participate in our hack. And so we started off by breaking into subgroups. So we had, I guess, 5 or 6 subgroups, and we tried to brainstorm, thinking rather optimistically, what are some of the different observations that we would love to get of a potentially habitable Earth-like planet. So just to highlight a few, here we have intelligent life, geoengineering, of course, yeah, spectral features of water and CO2. It would be great to get some measurements of the planet magnetic field, landmass distributions, oceans, ice, looking for habitability signatures, such as the presence of reducing gas for redox reactions, energy sources, surface spectral distributions, and also the insolation. Topography was another thing that came up. Mineralogical maps. It was great to get kind of the geoscience perspective and how kind of potentially mapping the spectral features and mineralogy of the surface could give you insights into the interior processes. Using polarization and glint, for example, to try to detect evidence of water, liquid water on the surface of the planet if it has an optically thin atmosphere. And then circulation in the context of planet climate and heat redistribution with Doppler measurements and time-resolved photometry. So after assembling this collated list of more than 50 different observables, I mean, there's some overlap, so I think all told we have roughly 30 independent suggestions. We then tried to prioritize to see, okay, what would be the top 10 most important measurements? And so, of course, we'd love to get the planet mass, surface gravity, and size. So some of this may be done with precursor radial velocity measurements. Stellar characterization was a big one, kind of getting a stellar spectrum. Astroseismic characterization, for instance, with Plato, getting the mass, luminosity, composition, activity, the XUV flux of the star, so that which has photochemical implications for the planet. Okay, trying to constrain the size of the planet. Of course, it would be great if we struck it lucky, like Beta Pic B's Hill Sphere, and see a long period transiting planet in the habitable zone, but maybe we can't better money on that option. And so other potential observables to constrain the planet radius need to be assessed. Talked a lot about time-resolved spectroscopy over the orbital period. A neat suggestion was to use stellar occultation by a directly imaged exoplanet to get a constraint on the exoatmosphere. We'd love to get the albedo of the planet, orbital characteristics from astrometry of the planet, the directly imaged planet's orbit, perhaps complemented with radial velocity measurements. We'd also love to put this planet in context to assess what are the other planets in the system, their properties, and how the overall architecture of the system in which this Earth in the habitable zone resides. Okay, and then surface composition from IR spectroscopy, looking for indications of various tectonic modes, plate tectonics versus stagnant lid, and what levels of detail in these observations would be important. And then also, it would be great to, we listed discerning whether there's liquid water on the surface as a priority as well. So then, to conclude the hack, we then brought the discussion to the topic of what should NExSS be doing now to prepare for making these observations and interpreting their results, and perhaps even prioritizing planet targets. And especially leveraging the unique interdisciplinary expertise that NExSS contains. And so we the group came up with a whole bunch of ideas. Here I'll highlight kind of three of the favorites that were prioritized among the participants in the hack. So one suggestion that was proposed, and this is maybe comes down to marketing a bit, is so there's a lot of talk about biosignatures. We should also maybe start referring to interior signatures, atmospheric signatures, technology signatures, because even if we have a biosignature false positive, well, that means it's a true positive for either an interior signature or an atmospheric signature. So kind of classifying the different signatures of planets in this way will give a more holistic assessment and also guide the interpretation of spectrally and time-resolved observations. The need for spectral and time-resolved observations was a recurring theme over the course of the hack. Another activity that we highlighted that NExSS could make a big contribution to is to explore and make predictions for kind of the processes of plate tectonics, interior dynamics on other exoplanets or rocky exoplanets. Constraining the existence of a carbon cycle, looking for tectonic signatures, what would be the signatures in the atmosphere or other observables that could be used to understand the interior properties and processes on distant exoplanets. So that's another area of research and inquiry that NExSS could pursue. And so the last one, the acronym is AABD, which stands for the Advanced Astronomical Bullshit Detector. And so here the motivation is, I mean, eventually we would like to see signs of life on a distant exoplanet. That's a big underlying motivation. But for any biosignature, there are false positives. And so what are the whole suite of observations that need to be made to rule out the false positives for any individual biosignature molecule or combinations of molecules that could be interpreted as evidence of life? So the AABD would be essentially a reliability assessment for biosignatures. So we should do a lot of the groundwork now before we have a potential detection of a biosignature in hand to try to understand what the false positives are and what are the necessary measurements. So one form that this could take would be essentially a data analysis challenge, to create a community challenge for biosignature interpretation, where perhaps we could come up with some biosignature scenario and then encourage geoscientists or planetary scientists or other people with expertise to try to come up with what their false positive scenario would be, and then we could assess what additional observations would need to be taken. So those were kind of a selection of the highlights from what I think was a great TAC. So I thank everyone who participated in the TAC for all their collating all their wonderful ideas, and am open to questions.
Thank you, Leslie, for the great summary. I just wanted to mention 2 points. So what makes this hack, I think, particularly exciting. So we had a great discussion, lots of ideas, as you see. I wanted to mention that this hack also directly feeds into the SAC-15 report, which is a study that's collecting community input from all of you and from others not in the room, the entire community, on what science questions future direct imaging missions should answer. So actually some of these questions will make their way to the SAC-15 report, which will have influence probably on multiple planning processes, including the STDTs for probably both the LUVOIR and HABEX mission. The other goal, of course, was to identify for NExSS exciting items that we should work on and connect it to other large-scale goals. So.
I can help with the microphone, Leslie, so you don't have to worry if I can get to it.
Yeah, out of those nine topics that you selected, I don't see the topic of the atmospheric composition. We know that if we really want to go after life, nitrogen is the most important. Yeah.
Yeah.
Yeah. So okay.
Yeah, sorry, it needs a number.
Oh, sorry. Yeah, right.
We had 5 minutes to prepare the presentation.
Okay, yeah, that's fine. Yeah, I just want to stress an attention about the nitrogen. So we probably need to learn, if we want to go for such a mission, learn from our Earth and from the 14 years of observations of Earth from space that observed, for instance, nitric oxide and observed the carbon dioxide in the infrared. Because we need probably, to go for life, we need to go for a beacon of life that tells us how life contaminated the atmosphere of Earth and what best signatures we see, emissions features, like 5.3 microns of the nitric oxide. And so we recently did some statistics of those events in response to the coronal mass ejection from the sun, and we have over 1,000 events. And those observations to looking at our Earth as an exoplanet in depth and to use all the available observations performed over the last 15 years would be very useful for this. Yeah.
Yeah, I completely agree. And let me just say that exploring planetary science techniques and looking at solar system analogs to exoplanets was another activity that was highlighted that NExSS could make a big contribution to. It just, in the interest of time, it wasn't one of the 3 that we chose to highlight for this presentation. But certainly the participants in the hack also had similar suggestions and recognized the importance of that.
Hey, Todd.
Did I miss rotation period of the planet anywhere?
That was included under time, resolve, photometry, and spectroscopy.
Okay. It'd be nice to call that out as a specific property of a planet.
Yeah, that was definitely included in this list.
Yeah, I had a similar question because presumably the timescales of interest would be different. For when you say time-resolved spectroscopy, you're not going to resolve, hour to hour because you just don't have enough photons. But you might for photometry, which is important for establishing the longitude distribution of landmass and water, right?
Yeah, over the course of the hack, there was some discussion of both day to night timescales, so timescales over 1 day rotation period, as well as seasonal timescales. And so,
seems more feasible. Yeah.
We didn't go into feasibility here. It depends a lot.
We're designing a 20-meter telescope, right? Come on, Sean.
Yeah. I think that any mission that is capable of looking for biosignatures will be capable of detecting diurnal variations without much problems. I mean, those can be pretty significant, and they can be done in integrated light. So I think that's my thought, but it depends on the architecture.
Yeah, just quickly, the things like the nitrogen abundance, that's all part of the bullshit detector. It's getting something that everyone buys into, because the worst case is we have lots of different claims of life detections, and this is too important.
We have time for one more comment if anybody wants to speak up. We've got 54 some odd things there, and it strikes me that a lot of that is just completely unfeasible for, I mean, we have constraints of technology, right? So what can we do? It really whittles it down to a tiny list. But I think what you find is when you do that, you're driving towards a bigger telescope, I think, is kind of the take-home message. It's the 3rd time I've tripped over that thing. Okay, Sean, you want the last?
So that whole group, and I think it was actually healthy, didn't focus on feasibility or specific missions or anything like that. There were discussions about let's get as many photons in as many colors with the greatest flexibility for the scientists to play with those photons as possible and bin them in whatever way they need to break a lot of the degeneracies. I do think the one thing that we also talked about is this may be more a list that encompasses, it probably is a list that encompasses more than one mission. And it would be good for the people in this room to think long term about even if this mission happens, it shouldn't be our last mission either. It shouldn't be our first and our last. It should be part of a continuum That goes back to at least Kepler. So.
Oh, it looks like we have an online comment. Eric Ford is online.
So Eric says, in the community challenges that I'm familiar with, there has already been a well-understood forward model. How would one design a community challenge for biosignatures when we don't understand the underlying physical processes? Good point.
I guess that's more of a comment and not a question. Yeah. Okay, it's 12:15, so I think we're going to move on. Thank you so much. Very interesting. So last but not least, we've got Kevin Stevenson, who's going to present on behalf of the JWST hack.
All right, thanks everyone. As part of the Transiting Exoplanet James Webb Space Telescope Science Hack, we did a variety of topics and covered a lot of different stuff in the time that we had. And so I want to just talk about a little bit of the things that we discussed and sort of the ideas that we came up with as a solution to the problems that we sort of are going to be facing with the James Webb Space Telescope. So I just want to bring... Yes, can you hear me? Okay, I'll hold it closer. Since not everyone is aware of the issues for James Webb, I thought it was important to be as informative as possible and bring everyone up to speed. For example, I'm showing here just a diagram of some of the spectroscopic observing modes available to the James Webb Space Telescope. And what you'll see is that it is actually quite complicated. Given the 4 instruments that we have, NIRS, NIRSPIC, NIRCam, and MIRI, there are a multitude of different combinations that we can put together in order to produce a transmission spectrum from, for example, 1 to 12 microns. And so understanding how each of these instruments perform and their capabilities, what the systematics are, what the brightness limits are, is a challenge that everyone needs to understand before they write their proposals. Because if you want to observe a JMAG of 5 target with NIRSPEC, for example, that may not be feasible. I'm not going to go. We're not going to go into detail here, but we did go into detail in the hack session as to what the different spectroscopic observing modes were and how that plays a role. On top of that, Natasha Battaglia is going to be introduced at the hack session, a JWST or exoplanet simulator. So if you have an idea of what sort of science that you want to accomplish, and you don't know how many observations you're going to need, the current technology that's available to us, for example, with HST, is not geared towards exoplanets. And so this tool is going to enable you to input in your configuration, whatever it is, whatever planet or system you're interested in, and you can input in a model of what your planetary parameters are, what sort of spectroscopic features you might expect to have based off of the scale height and the cloud coverage. And it will, and based on the telescope or instrument that you want to use, how many observations, it'll output the spectrum and with error bars so that you can evaluate how many observations or how much time you might need to produce your science. So this is an excellent tool that will be coming available in early June. Natasha is the lead author on a paper that's going to be released, and the simulator will be available through the Penn State website. Look for the paper, and this tool will hopefully be very useful to everyone who's interested in James Webb, observer, theories, modelers, everyone. I really encourage you to take a look at that, and so we talk a lot about that in the discussion. From there, we wanted to move on to the early release science program. And so let me motivate this a little bit by introducing the problem that we have with the James Webb Space Telescope. So we're going to be launching in October 2018, give or take. And there should be about a 6-month commissioning mode. And from there, observations will begin approximately in April of 2019. And what happens is when you get your data, most of the GTO and the Go programs are going to be are going to have 12 months of proprietary period with their data. So no one outside of those programs will have access to that data, and they will not be able to understand the instrument systematics and based off of that information then propose for cycle 2 data. So the proposal deadline for cycle 2 is going to be somewhere around December of 2019. And so there'll really only be a couple months worth of data, and most of that will be proprietary. So this is in fact a very big problem. If you want to be most efficient with the James Webb from the very beginning, we need to have access to the data as quickly as possible. So that's where they came up with the early release science program, is that it'll essentially seed initial discovery by quickly building experience on these data sets that everyone can then work on. And really what it is 500 hours of telescope time that's allocated at the very beginning of cycle 1. And as a community for transiting exoplanets, what we want to do is get together and decide what are the biggest priorities that we want to resolve with this early release science program. And that is the heart of what we talked about in the hackathon, and try to come up with different ideas, review the ideas that have already been proposed, but come up with new ideas as well. What are the key data analysis challenges that we're faced with moving forward, and what we want to resolve. So there are a list of planets, I'm just going to show them to you here, that are what we consider community targets. And these planets themselves are what we would say are ideal or the best candidates to look at for transiting exoplanets, simply based off of a certain parameters or requirements. For example, they have to be visible, they have long visibility windows in the sky, short orbital periods, orbit around bright, quiet host stars, that sort of thing. And so what we wanted to do is find out what are the major questions that we want to have answered at early release science. So one of the important things are instrument systematics. That plays a huge role in understanding how the instruments are going to behave and which ones will behave the best. So that is so one of the things that we have, our programs that we talked about moving forward would be looking at one of these exoplanets in all of the available observing modes. So if you really want to compare near-spec and near-cam to nearest to MIRI, and look at the overlapping wavelength regions to see how each of these instruments perform, then what we really need to do is look at one target and all of these modes and then compare apples to apples. And that'll give us a great baseline of what we're looking for in terms of the systematics and the performance of each of these instruments. Another question that came up is stability. So how stable are these instruments over what time frames? Do we want to look at a planet or a system for 24 hours to test the stability of not only the system but the instrument itself over that time frame? What sort of questions or systematics arise over that period of time? One of the other questions that came up is that of repeatability, and that was one of the ones that we really wanted to focus on here because it wasn't addressed in the white paper itself. So if we want to really push the limits of James Webb, if we want to look at some of these super-Earth or maybe Earth-sized planets orbiting early to mid-M dwarfs, if you want to look for habitability, say, then you really have to push the repeatability of the instrument to well below the noise floor. So that's one of the questions that we think that really needs to be answered that hasn't been addressed up until now. So we sort of put together some ideas of how to move forward on that. What type of stars, for example, we might want to look at. Should we focus on G-type stars, or maybe we want to focus on the M dwarfs? What's the repeatability going to be both from an instrumentation point of view, and what's the repeatability going to be from an astrophysical point of view? Because those are two different questions. We may have a quiet star. We may have a quiet instrument that will behave, but if we don't have a quiet star, then we will not be able to push down to the limits that we need in order to characterize the atmosphere as well as we'd hoped. So this is really important questions to what star we pick for this particular type of test. And if we can push below the noise floor and prove that we can do that with early release science, then we can come back at cycle 2 and start proposing for larger programs that will require a large amount of time. So for example, for James Webb is only nominally 5.5-year mission. And so if you want to look at a Earth-sized planet, sort of 1 to 1.5 Earth radii, you will need to get many visits. We're talking about on the order of 40 or 50 visits just to push down to, if we think we can actually beat through this noise floor. And to do that, you're going to need, for 40 to 50 transits, you're going to need several years worth of data built up. So if you want to complete this single goal during the lifetime of the nominal 5.5-year lifetime of James Webb, you really need to start pushing it as early as possible. For example, cycle 2, which means we need to understand the instruments well in advance of that. So cycle 1, at the beginning with the early release science, this will really push towards that goal. And one of the final questions that we looked at was the brightness limits of these instruments. How bright can we go? Because of course, the brighter the object is, the more photons we're going to get. But there's also specific challenges in terms of the instruments and the observing modes and the efficiencies. And so we kind of looked into that as to different ways of being more efficient with our time and getting the most amount of information based off the plans of these observations. So that's just a rough sketch of the ideas that we came up with for the early release science program. If you're interested, we can talk about it in more detail. I didn't want to give you guys all the juicy details that we talked about there, but at this time I'll open up for questions.
Any comments, questions? From an online person? Okay. Who is it? Eric Ford, will the host stars for community targets to be observed intensively have been pre-screened to be stable stars? How and to what level?
Okay, so all of the planets from the community, all the systems from the community targets have been looked at. They're either WASP or HAT targets. They have been monitored. They have their masses measured. We do have estimates for their stability. Some of them are photometrically more stable than others. So we're creating a table. We're currently working on getting specific values for each of these targets. So that is a work in progress. The other aspect that we have to look at is the possibility of clouds in these planets. So if we're trying to do transmission spectroscopy observations, it would behoove us to have a target that has spectroscopic features. Not only is that scientifically interesting, but it's also it advertises well. So we don't necessarily talk about this all the time from exoplanets, but it would be really important for the exoplanet community as a whole to have an early release science target that produces a beautiful spectrum with large spectral features that everyone can look at and say, wow, look at that. There's water, there's methane, there's CO, whatever it is, whatever we detect. And that will go a long way towards advancing exoplanets with James Webb by increasing the excitement level for exoplanets. So we are in the process of pre-screening the community targets with HST and Spitzer. There are proposals in to get time to look at them to make sure that they do in fact have clear or relatively clear atmospheres and hopefully quiet host stars.
Any other questions for Kevin? Yes.
Oh, I was just curious, are the locked up geo targets known? Is that list available?
Okay, so the guaranteed time observations, the proposal goes out, I believe, in January of 2017, and they'll be locked down, I think, in March or
April, yeah.
Yeah, the timeline's there. So GTO Cycle 1 called for proposals in January. Proposals are due in March. So we will need to work with the GTO teams and make sure that our targets and observations don't overlap with their targets and observations, so that we can't have overlap. So we have to work with them to make sure, and that means that we actually need to identify, of the 12 community targets that I had listed there, which 2 or 3 targets that we want to pick for the ERS program and identify that prior to March 2017. 2017.
Yeah, we can't observe anything that's on a GTO target list. So there's a lot of pressure for them to identify their targets as soon as possible. Yeah. Thank you, Kevin. I think we need to move on. We're bumping up into lunch. I think, Ravi, did you want to say a few words about the photochemical modeling?
So we had an overwhelming group of people, maybe two or three, and the photochemistry model. So my idea was to actually get. I'll be quick. I know everybody's hungry. So we try to get a couple of experts within the Nexus team to collect and see if we can think about a multidimensional photochemical model. And the couple of people that we just talked about are Eric Cabrera and myself. And I'd like to talk more about this with Nexus group team members who are involved in the GCM simulations, and then take it much forward during our Nexus team meetings. So this is a process that needs to be continued later.
So I would say that we'd probably have one in the Rocky 3D team if I had gotten my act together sometime in the last 6 months. And we do have one with the Rocky 3D team, but it would be a generalized planetary one if I had been able to spend more time on it. So look forward to that. And I would say talk to Tony about that, and Kostas, who's not here in person but has been online the last 2 days.